Good afternoon, everybody, and welcome to this session. Today we're just going to talk about how overlays work and how we connect our VNFs to NFV clouds and from NFV clouds all the way out across the overlays in the wide area network, and why you would want to do that, indeed. So to break that down, we're going to talk about what overlay networking is and how the overlay networking works, how we put together those overlays using various technologies, including BGP, to make the overlays work well for us, and how they can be implemented within OpenStack. So just a quick introduction about overlay networking, and the first question to ask is why we would ever use overlay networks in the first place, because they do make things kind of complicated. So the reason we do is because actually, as well as making things complicated, because you've got an extra layer to debug, but they actually make things slightly easier, oddly. What we do is we take a network that could potentially involve a lot of devices in it, and we say, right, we don't have to worry about that. What we're dealing with is very, very simple. So we have a tunnel endpoint or a group of tunnel endpoints that we connect together in some form of mesh usually, or a VTEP if you're using VxLAN, because they're awkward and they use a different term for it. And all of that question about routing and whatever goes away. All I have to worry about are the endpoints on my virtual network, which makes my life much easier. It also gives me some power to actually engineer where the traffic goes as we go. So why is that not working? Never mind. Right. Why would we want to do that? Here's one example. This is VNF at the WAN edge, right? So I have a cloud at the edge of my wide area network, somewhere near my customer. I'm doing things in a VNF, and for whatever reason, there's a useful reason why I want that close to my customer. One answer to that is if I'm doing radio access networks, so that's the mobile radio that actually connects your handset, and I'm doing that with a VNF, which is one of those things that turns up in 5G, then it's got a bunch of traffic. It's got to be very close to the edge of the network, because you've only got about 15 kilometers range for it to work, for it to be able to control a radio. So you can control radios in a 15-kilometer circle, but I might want to do my actual traffic processing further back so that I'm doing it in fewer sites. In order to do that, then perfectly reasonably, I might want to basically wire a virtual overlay that takes the traffic from the edge and brings it back to the site a little bit nearer the center, where I'm going to convert it to IP traffic and work out how much to charge you for your mobile connection, because, you know, money. Alternatively, I might want to be doing something with a data center overlay. So the biggest problem we run into in data center overlays is we love, and well, right? 30 years ago, someone loved VLANs. Someone worked out that all I need to do is basically use a VLAN tag, and that gives me effectively, it turns one wire into about 4,000 wires that I can use independently and separately, and that's great. They also worked out how to make sure that I don't end up with packets going round in little loops in my data center, which usually ends up with a packet flood in your data center and upsets everybody else using that data center. I may have done that at some point in the past. I wouldn't recommend it. In order for that to be prevented, there's a thing called spanning tree protocol, STP, that prevents loops. But modern data centers tend to use an architecture rather like the one that's up there. So I have a spine and a leaf architecture, and I wire it together in a clos fabric like that. It's full of loops. If I use spanning tree, it starts disabling a bunch of those links, so there's not a loop left in the whole diagram. I don't actually want it to disable those links. I want to use all of them so that I get the maximum bandwidth. So a modern data center uses a layer 3 fabric. I do routing in there instead. But I still want to use potentially layer 2 between my endpoints, between the leaf ports. And in order to do that, I'll use an overlay like VxLAN. So that allows me to have layer 2, but it also allows me to use layer 3 on the links, which means that I can get the maximum benefit from those links without having them all shut off by the layer 2 management protocols. Layer 2 scales poorly, layer 2 scales to thousands. So overlays in the data center and the WAN. What we're looking for here is we're looking for multi-tenancy, meaning that I want more than one overlay. I want to keep these things separate. I'm looking for an increasing quantity of scale. So I expect these things to have a bunch of endpoints on. I expect my WAN to be, rather large, considering that it's got to provide for thousands, potentially millions of customers. I would like seamless mobility, which means that if I find that my VNF is suddenly somewhere else because there's been a failover event, then my overlay deals with the fact that an endpoint has moved. I might be dealing with traffic east-west, which is basically in a data center, in an OpenStack cloud, for instance. So that's server workloads with generally talking to each other, but also north-south. So I'm talking across the WAN to other data centers, to customers. And I'm looking at these networking options. These are the ones we're going to explore today. VLAN, we've discussed, not terribly scalable, certainly doesn't reach across WANs today. VxLAN is a perfectly good protocol using IP. MPLS and segment routing use things that are not IP-based, and SRv6 strangely combines both of those together. So those are technologies. We'll talk about these three in a bit more depth and give you some examples about how they work. So how do we make them work? Well, if I want to do this, then one option is I make my tunnel endpoint a piece of software. We've all talked about things like OVS down here at the level of on the hypervisor as a piece of software. You can work magic with OVS, you can work magic with VPP. Each one of those supports a variety of overlays. OVS will do VxLAN, it will do Geneve, which is VxLAN, very like VxLAN. VPP will also do a bunch of MPLS of SR overlays as well as VxLAN. And I can do a great deal of things in software. The joy of software is, well, there might be a bunch of standards out there, but if I choose to implement it slightly differently than the standard says, because I'm within a cloud and maybe I'm keeping my little inconsistencies to myself and nobody has to know about it, then I can add little features to that, control it slightly differently. Many types of overlays are supported, and we're on software-based limits, which can mean potentially that I have a fundamentally unlimited number of ports that are connected to my VNFs down at the bottom. Software scales, so if I start making VNFs, it's just another data structure in my memory. But another alternative here, and this one is kind of useful, is a hardware-based tunnel endpoint. So if I start with my WAN network here, so these are provider edge networks, devices rather, then I make my tunnel endpoint on those devices. And that's magical because now instead of burning CPU in order to get things to work, I get to use no CPU already. I get to use a feature that's already in a router at the top there. That is, and all I do is turn it on. I need to make it work in coordination with my software, but I don't necessarily need to do the work in my software. And that works with PCI pass-through. And PCI pass-through devices allow me to run VNFs faster. They do a bunch of things like memory copying that otherwise I would be burning CPU on. So I get the bonus, I'm not doing the encapsulation in software, which is cheaper, and I get the bonus that my VNFs run faster as well. So that means I get more power out of each individual server. And pros and cons, right? Better performance than VNFs, high throughput, low latency with my hardware VTEPs, hardware tunnel endpoints. I always like that sort of thing. But it does limit me in terms of scale. It requires a TOR that's potentially top of rack, that's potentially more expensive than the one you would normally buy. You might not be buying a white box top of rack switch. You might even be buying a router and putting a router at the top to get the level of support that you're looking for. And obviously, now my forwarding's implemented in hardware, so if I start stepping up to a new kind of overlay, then maybe a hardware upgrade is required. But whereas a software one is completely flexible and horizontally scalable if I want many virtual machines to run, but I do burn CPU to get it. Now, CPU will do the job. CPUs are not as cheap as they might be, so that's a limitation. And it can also be slightly difficult to troubleshoot because software tends to go wrong in new and interesting ways, as any software engineer knows. So, isn't this easy? Well, where do we?
Yeah. Okay. Overlay networks are usually great. It gives us a lot of benefits. It gives a lot of useful cases. But there sometimes it's not easy, and we have problems with overlays. So I'm going to simplify this into a very easy diagram. So we have, say, 3 V switches. They're connecting in the internet, over the internet. And I'm drawing a 3 tunnel ending point here. And tunnel is basically an end-to-end connection. Means that they have a specific, you have to do a source IP and destination IP. It's end-to-end. So in this case, I have to end from A to B as end-to-end. But there are always some traffics in BOM. We call it broadcasting and no unicasting and multicasting. And some type of this traffic happens all the time, like ARP. So how ARP works basically is I sending a broadcasting packets, and whoever has the MAC just responding, so you can make the connection works. So it's this model we kind of knowing as a flood and learn. So this is a very common mode. And in the traditional network, like in LAN, so we can manage, it's manageable. Like in your LAN, probably just like 100 nodes or a couple hundred nodes, still manageable. So flood and just works perfectly well. But when we talk about overlays, this thing's gonna be amplified a lot and then can cause a lot of unnecessary traffic. So I can give you examples. So for example, the left side you can say, imagine there's like a San Francisco, Beijing or Shanghai, there's a Shanghai side here. And on the right side, we got like say San Francisco and say New York. So in this case, if one VM on the Shanghai side want to talk to someone in the New York, because it's flood and learn, so I don't know where my VM is. So in this case, what you're gonna do is have a one packet coming, going through the internet. So internet will ask, okay, I have a flooding packet, I have a broadcasting packet. What do I do with it? You're gonna flood. So in this case, one single packet becomes n packets. In this case, means that if both your San Francisco data center and the New York data center are gonna have this traffic. You can see this amplifies huge, and so you can see a lot of times it's just unnecessary. It's gonna work, but just unnecessary. So this can cause a huge quantity of traffic. That's just one big problem. And also another basic question we're gonna ask is, how do I even know where to send it? Say for example, now I have like 3 sites over here. Say tomorrow I gotta have a Chicago, say some site coming on into commission. Then we're gonna understand, okay, in my flooding list, I also need to add in that Chicago site over there. So you can see there's a ton of ending point discovery thing. So we don't even know where to send. So I need to know that up in front. Okay, I need to talk to 3 guys, or I need to flood to 3 guys. So there's like no automatic discovery because they're all end-to-end connections. So we have a problem with it. And how do we solve the problem? BGP-EVPN that's the perfect solution. And it's address the question, how do I get where I'm going? So I'm putting these slides here just not to scare you guys, because there are a lot of information here. But I'm just giving you the point how this thing, being coded in the actual packets. And for the BGP-EVPN standard, we have a total type of 11 message types, I think, as of now. So they're for different purposes. But in order to solve our problem, we only need 2 of them. So type 2 and type 3. So type 2 is called MAC IP advertisement, and type 3 is called inclusive multicast Ethernet tag. You don't have to go all these details, and I summarize it for you. Type 2 message is the information about host. Say, for example, I have a new VM coming into the San Francisco, I have a new VM coming to Shanghai. The BGP speaker will speak something, okay, I have a new VM, and they're gonna speak type 2. So the remote guys will know, okay, there's some guy in the remote, is, so that I don't need to send in a flooding message, like ARP. I don't need to do that anymore because I know that this guy is on that side. So I don't need to flood, so I can save a lot of flooding traffic. So when any VM comes up online, we have a type 2 message. Type 3 message is the information about overlay. So it means that you have say today you have a 2 data center in United States, and tomorrow have a new Chicago. Okay, how do I know there's a new guy? Type 3. So type 3 you're gonna tell the remote guys, okay, I have a new VTAP coming, so please adding me to your list. So it's information about the overlay. So if you combine the type 2 message, type 3 message here, you're gonna solve the problem perfectly well. By solving you can get rid of a lot of unnecessary flooding. It's gonna be much more efficient. Now I'm gonna hand to Vasu to go through some of the overlay technologies.
Okay. Thanks, Ichan. With that background, let's take a closer look at what these overlay technologies can offer to us, and then let's compare, one with each other. So first in the list is VxLAN. So, with the growing, server virtualization market, and there is a lot of, things happening in the cloud computing. Actually, the demands on the physical infrastructure has grown tremendously. So, cloud providers would like to address the scale that the multi-tenancy is actually bringing to the table. So VLAN, one of the oldest ways of actually providing the network isolation wasn't really a match for the growing needs of cloud. So let's see why VxLAN even was designed. So as you know, the VLAN header has only 12 bits, and it can address only 4K network isolation, and that wasn't really going to help, and they wanted to have something bigger, and that's exactly why the VxLAN header came into picture. So if you see, the VxLAN header has a 24-bit field, which is a VNI, which is going to uniquely identify all your logical networks, and typically that's the scale that you would want to support in a cloud. And also, for providing the elasticity in the cloud, you would want to really distribute your workloads within your data center and outside your data center. And how would you do that? So you want to do a layer 2 stretch, and how the layers to stretch can be achieved. It can be through an L3 fabric, and that's exactly how VxLAN fitted in the picture. So you don't really need to run any control plane protocols for VxLAN to be supported. So it's all taken care by the L3 fabric. But what you need for VxLAN to be deployed, so you need all the VxLAN endpoints, or the gateways where you would want to terminate those tunnel endpoints. So it can be offered by a hardware device, or it can be offered by a software device, which we kind of saw earlier. So let's see. Let's see. Okay, so let's see some of the shortcomings of VxLAN. So because there is an extra bit of an overhead involved in actually doing an NCAP here, so there is a bit of 50 bytes header involved, and that's something that adds as an addition to your original payload, and that's that's something that you would want to really address in your physical infrastructure. So for that to be accounted, you need to be able to support your jumbo frames in your network infrastructure. So that's one thing that we got to live with it. And then the next thing is it doesn't really give you an ability to actually do the traffic engineering, because that's something that you would really want to have on a overlay technology. And let's see how how we can actually get that benefit out of MPLS, which is one of the other technologies we're gonna look at. So MPLS has been in existence for so long, and everyone, every service provider loves MPLS because it's highly scalable. It has only 4 bytes, and out of 4 bytes you have 20 bits for the label, and the rest is all for the QoS and the end of stack, and it's pretty tiny header size. And if you want to deploy an MPLS data path, you need to have the control plane, and the control plane can be signaled by an LDP, RSVP, T, or another BGP multi-protocol. And it is highly scalable, but it is very hard to manage because all the labels that are distributed in your backbone are locally significant, and it kind of gets difficult to actually understand and troubleshoot how these labels are mapped into different routers. So that's how MPLS works. And let's look at the definitions. So here, if you see, there are this 3 main components in an MPLS network. One is the label edge router, where you are actually doing an NCAP. That router is responsible for adding a MPLS header on top of any transport, and that's called the label edge router. And the router in the middle is the label switch router, which is going to swap your inner label with the other label with which it's going to get to the next router in the network. And then there are these label functions, which I kind of briefly talked about just a second ago. So the push is what is doing the NCAP, and the swap is the operation that you do when you want to forward the packet through the MPLS backbone. And then the pop is the last operation that you see before the PHP. So if you want to reach that prefix over on the other side of the network, it's going to do an NCAP on the LER, then there is a swap, and then there is a pop, because it's the penalty hip hop. So you do a pop, and then you save a label lookup, and then it just goes directly to their LER to do the IP forwarding. Then that's how MPLS works. And why it is scalable? Because the backbone really isn't really impacted because of the as you have more and more customers, it doesn't really impact the scale of the MPLS backbone. That's one thing. And the other thing is, because it's 20 bits, it can address that many, overlays. And if you add on top of, the existing label with another label, then you have like a million square tunnels, which is quite a huge number. And you can actually play with all the, circuits and other features. And that's one, benefit you get out of MPLS. The other benefit you get out of MPLS is because traffic engineering is a very important, feature that this technology offers. Because if you want to really, steer your packets into a certain circuit path, you just do that with the label stack, and that's, that will kind of get your packet to the final destination. And there is something better, which is the segment routing. The segment routing is something new, but it really works on the IP technology. So basically, for the segment routing to happen, you need to have an IP domain, and it can happen on an MPLS network as well. So there are two things that segment routing uses. One is the MPLS data plane, and one is the IPv6 data plane. And for the MPLS, you don't really need extra, it just, as long as your network supports MPLS, it just requires your, it just requires a software upgrade for the segment routing to be deployed. And let's see some of the terminologies and how segment routing actually works. So in this diagram, you see there are like a few nodes, and basically the way that segment routing works is you kind of assign a label to a particular node, and it means that if you want to really get to that particular node, you push a label on top of a packet, it gets you there. And your routing protocols is going to give you all the reachability for that label path. This label encoding is all done, through routing protocol, or it can come from a controller. And the advantage of segment routing is that you don't really need to run any special protocols for the label distribution. So you kind of encode all the information inside the packet header, and the packet header will carry some list of ordered segments. With that, you can pretty much steer your packets in your SR domain. And that's a great benefit it brings to the table, because you really don't want to deal with a lot of states inside your network. And as long as you know where exactly you need to steer the traffic in, you can pretty much encode all the instructions inside a SR header, and this put it in the network. So here, let's take a quick example on how BGP as a control plane can actually help with the SR data path. So as you see, I've actually zoomed into that network to actually show you an example of how the packet is going to get to node 11 from 1, right? So basically, the assumption here is you are actually running a BGP peer between each nodes in the clause fabric, and it is actually going to advertise the labels in the SR domain, and there is an extension that we have to actually tell the router what the SR index is and what the label base is, so that it kind of computes the SR identifier for you, and then it kind of puts it into the BGP to actually distribute that information. So here, if you want to, reach node 11, node 11 sends an update that, hey, I have this prefix, and this is my label, and this is an implicit label because it's the last hop in the network, and the AS path is 11, and it just sends it to the a neighbor, and the neighbor is going to compute the label 16,500. Here 500 is your index and 16,000 is your SR base. You just add that on top, and then it kind of computes the label, and this is a global label in this whole SR domain. And this is a little different from how MPLS worked before, because in MPLS network all these labels are locally significant, and here is a global label, which kind of helps the operators to really easily troubleshoot the network. That's one thing. And then it does send the update to the node 7, and the node 7 is going to tell, hey, to reach 10, this is the label, and he's going to advertise it to node 4, and this just happens again, and it finally, the router 1 in the, this is the top of the rack actually, 1, that knows how to get, the packet to the compute, which is on the other side, and it's going to go through the clause fabric through this segment. And this one segment, 500, actually tells that you have a path from 1 to 11. And now, so now, let's see how, why traffic engineering is important. And let's understand why, SR actually helps with traffic engineering. So basically, in this diagram, you have one Shatas path, which is actually a path that is given by your routing protocol. So from A to C, you have all the costs that are costs that's configured, and your routing protocol kind of computes your shortest path, and it gives a label for that shortest path. It could come from an IBGP, or it could come from a BGP, whatever it is, right? So, but that there is another link that exists between A and C, which is a low latency link, which is completely different from what your routing protocols can actually provide you. So with that information, if you want to really steer your time-sensitive traffic, then it really works out well for you in some cases. So that's where that's how you actually do traffic engineering. So another thing to look at is basically, if you have an ECMP path on your networks, you can pretty much have both the long-lived flows and the short-lived flows hashed into the same link, which can cause some traffic imbalances in the network. So you don't want to really, end up seeing that, because some of your applications may need some high-performance connectivity. So with traffic engineering, you can actually steer the packet flows into the segments that you want to steer the packets into. So that's that's something that MPLS and SR provides together. But here, why is this relevant to the edge cloud? And actually, I didn't. I don't want to really go into the details of how these VNFs are actually, placed, because it doesn't really change the fact that these VNFs need to be chained. So as you see on the far to the far edge, you have these radio stations, and there are some VNFs placed. And then in the regional center, you just take the traffic, and then you need to chain these VNFs, and then the traffic goes all the way to the core, and all these need to be chained. And how would you do that? You typically do that with an overlay, and here the overlay could be an MPLS, or it could be SR. So that's exactly why SR and MPLS are interesting in deploying your in the deployments of these VNFs. So with that, I am going to hand it over to Echen so that he can actually continue with how these things work further.
Sure, thanks, Vasu. So we learn what is overlay network. We learn what value it brings, and we learn the problem, and also we learn how they works. And now the question comes, how if we want to do it, how do we want to do it in the OpenStack context? So basically, we are breaking into three parts for implementing any overlay. So we need a control plane, and then we need a FIP, and then we need a data plane. So there are three key components. So let's do a little deep dive on this. So the control plane we mentioned before is basically BGP-EVPN. And that's we need, in order to have this control plane implemented, so we need a BGP speaker. So the BGP speaker here is basically to resolve the overlay reachability information over the EVPN protocol. And sometimes you may need underlay reachability as well if you're using MPLS or SR MPLS. And the common part between all three overlay technology we mentioned here, VxLAN, MPLS, SR, SRv6, they are all basically BGP-EVPN. So that's a very, pretty much the standard protocol where we handle the overlay reachabilities. But for the underlay, they are slightly different. And for the underlay, VxLAN is a matter of IP routing, and whatever IPv4 or IPv6 underlay is, do with it. And MPLS, the underlay is MPLS, and you have to get a backbone, MPLS backbone network in order to use the overlay with also SR. And if you want to handle the underlay, so we basically, we need also BGP-LU labeled unicast, because we need the underlay reachability. So on this transport label exchange, it's all over the BGP-LU protocol. And for SRv6, and the underlay is IPv6 routing. Segment routing with SRv6, by the way, is segment routing over the IPv6 fabric. So little enhancement and over the SR MPLS, and we're gonna go a little more detail on it. And the FIP is normally, once with control planes, BGP speaker. It has all the information learned over the EVPN. But we need to store it somewhere. So we learn the overlay information and then store it in our database. And this database is not gonna be a very fancy one. It can be as easy as a key value database. So little recall on the EVPN type messages. So type 2 is basically information about a host, and type 3 is information about overlay. But in order to more summarize it, and type 2 gives you 4 information. Which VM with which IP is on which VNI is on which VTAP. So it gives you 4 information, little, wrap, but you got the point. And information about the host, like a MAC IP, and information about tunnel, VNI, and VTAP. And for type 3 messages, it just tells me which VNI is at which VTAP. So if you take a little closer look on this, so type 3 message is kind of a subset of the type 2 messages, as type 2 gives me both tunnel and the host, while type 3 only give me the tunnel. So in this case, by a little more abstraction, we can inventing something like key value. So key gonna be some VNI and the VTAP, and the value gonna be a list of MAC and IPs. So I'm not saying this is the only way you can design your FIP, but I just show you the idea. This can be as easy as a key value storage system for your FIP. And that's all we need for the overlay now. Every information, that's all we need here. And data plan. Let's go over a little more on a data plan. So data plan, as we mentioned previously, and if we have a hardware tunnel ending point solution, and the Tor does most of the heavy lifting for you. And the Tor understands what is BGP, Tor understands what is SR, and Tor understands what is VxLAN. So Tor does most job for you. And in this case, they're putting data plan here, and it's just for your software. If you want to do the same thing, what do we do in the software? And for the overlay payload here on the third column, and they basically everything is IP packets. So your all Ethernet packets is for your actual payload in the overlay network. But for the underlay and overlay header, of course they're different, slightly different. And in the case of a VxLAN, the underlay is just IPv4 and IPv6, and the key part is VNI, which is in the VxLAN header. So in this case, if you want to implement it, you have to do like a vSwitch or your Tor. Need to understand how to encapsulate VxLAN and how to decapsulate VxLAN. That's your Tor or your vSwitch need to understand. And for SR, and it's a little tricky, and because for underlay and MPLS for sure, but there's no meaning of the overlay header, because in the case of SR MPLS, a segment concept in SR is nothing just better MPLS label, and a segment list is also nothing but an MPLS label stack. So we can say everything. There's no additional concept over here. Just the way that we define them is different. How do we map them into MPLS? So there's no overlay additional header for the vSwitch to encapsulate or decapsulate. And for SRv6, also things also I would explain a little more on this. And SRv6 is segment routing over IPv6. So underlay has to be IPv6. That's the pre-requirement. But how this overlay works, so in the IPv6, so we have something called SR extension. So this all the pure IPv6 packets, but we are inventing something with extension. And this extension, we have a choice here. So basically, when we go to the IPv6 fabric, and if the routing node in the middle, it can't understand SRv6. We call it SRv6 aware node. If this aware node, it can do smart things. Basically, it can understand XR extension. It can do traffic engineering, and all this SR specific and smart things if you do the SR extension. But of course, if your fabric, IPv6 fabric, there's some node over there, cannot understand SRv6, that's still okay. So this node just probably simply just dropped SR extension. It doesn't read the XR extension. Just do the regular IPv6 routing. So you can see if you're doing SRv6, it's gonna be for production or for deployment, gonna be a little easier because it can make it either SRv6 aware node if you have a smart equipment. Just make it a regular router over there. If there's make it SRv6 unaware node, it's let it do the regular IPv6 routing. Okay, quick cap on this. How do we implement? How do we really do it? So we have three things we'll talk about from the OpenStack point of view. So we need from the point of a Neutron server, and we need a type driver. So Neutron has a built-in support for VLAN and VxLAN and the GRE, all this type we are pretty familiar. It's their built-in support. But as we are inventing something, so we need a new type driver. So in this case, you can call whatever name you want. You need just need a new type driver. So in this case, you can do a Neutron network create -- physical network type. You can say SR EVPN, VxLAN EVPN. This is the new type you're inventing. And then now we have an overlay FIB. That's key value database, and we need this database sitting in the central because it's interacting with both BGP speaker and our vSwitch agent, basically our control plane data plane over there. So on the control plane, the BGP speaker can exchange the EVPN messages and maybe also LU in the case of SR. And they basically save the remote route into the FIB and also advertise the local changes to the remote peers, like exchanging the overlay information. So learn if somebody in the remote happens or advertise something when we local happens. So basically bi-directional exchange. And of our data plan, we just need to enhance a little bit. And when there's a port binding and unbinding, basically means that you have a new VM or deleting a VM, you need to adding or deleting some entries from your FIB to reflect what is happening in your local, so that the remote guys will pick up and say, okay, some VM goes away or some VM is coming. And also we need to react to the FIB changes and by delete and create a remote tunnel ending point in vSwitch, and also for this basically consuming the type 2 messages, and also this one also need to consume type 3 messages, basically reacting to the EVPN changes, so we can implement the vSwitch. And for the hardware, it's much easier because hardware handles the control plane data plane for you, because hardware is normally your Tor, and it can speak BGP for sure. It can also do the VxLAN encapsulation, decapsulation. It can also understand SR. So all this heavy thing, they're done in the Tor. But again, from Neutron server, you still need something for Neutron to understand you are inventing something new. And then for the BGP speaker, the Tor does most of the things for you automatically. And the only thing you need additional in your Tor agent. So why we need that? So like a picture over there. So for example, we have a 2 VNF connecting to your Tor. So they are on VLAN 100 and a VLAN 200. Remember the picture we're showing in the back. So in the case of a hardware tap, and the connection between your hypervisor to your Tor is a layer 2 link. So layer 2 link means it's a VLAN. But Tor speaks VxLAN or SR. So you need to translating from the layer 2 into layer 3. So do this kind of encapsulation for you. Then how does it gonna do it? So it's gonna say, for example, Tor need to know, okay, for VLAN 100, this is the VxLAN overlay. It's transferring to VNI 5000. So we need to maintain this kind of a translating information. That's what our Tor agent's doing. So providing this translation information into Tor. So Tor can do your packet smartly. And the same thing for VLAN 200, okay, Tor may understand, okay, this is an SR overlay. I'm gonna translate into a seed label 16500, something like that. So you need a Tor agent to do the job for you. Okay, good. And that's a reference we are using. And any questions? And thanks for listening. Thank you. Welcome questions. This guy? Oh, reference. Okay. There's some public information. Just put it in the reference.
Some of this is implemented. We between us, we work on the Cisco Vim product, which is a virtual infrastructure manager used for NFV, and we've implemented both VxLAN and some SR into that with software switches, and we're looking at the hardware switch side of things. We've already got some code in that as well. So yes, we have implemented these things.
As you migrate a VM from one node to another, how do you update the information for labels and routes?
So if you're doing this with software, then your tunnel endpoint is actually the virtual switch on whichever host it's on. So if I move my thing from host A to host B, then effectively BGP is a big database. It says that endpoint, that virtual machine is at host A. Now I have to say, hang on, it's not at host A anymore, it's at host B. So I would update the fib internally to say, now this endpoint is on host B, and then the BGP speaker would learn from the database that it's on host B and would issue the appropriate withdraw and update update in this instance to say, go over there from now onwards. Then all of the other hosts learn that because they're listening to the BGP messages as they're propagated. Yes, so you've got an unbind and a bind as far as Neutron's concerned. It's unbound it from host A, and it's bound it to host B. So unbinding it from host A is a withdraw, and bounding it to host B is an update in BGP. Sorry? Right, the question is, did we think about using OVN? In our instance, when we were implementing this, we used VPP because we were trying to do specifically fast NFV networking, and we find that VPP works better. It's better suited to the number of flows that you get in that kind of networking. I imagine you could also do this in OVN. It's just a matter of programming a certain set of rules in based on what you've learned from BGP, so it's certainly possible. I'm not enough of an expert on OVN to say how difficult it would be, but you could take that to, I suspect guys at Red Hat would love to talk to you about that subject. Okay, thank you everybody, thank you very much.
Thank you guys.